Today I'll walk you through the implementation of Monotoinc Writes session guarantee on top of eventually consistent system. The implementation will be based on this article, which is provided on the screen. It's very good and concise, and I definitely recommend it. My name is Ivan Fedyanin, I'm software architect, and on this channel I'm doing series of videos about distributed systems. Let's start with short recap of the definition of Monotoinc Writes. And if you want a more thorough and full definition with explanations, just refer to my other video about client-centric consistency models. On this picture, we have a distributed storage system which consists of 3 servers. There is some replication happens between the servers, but for our purposes, it's not important which algorithm of replication is used. Only we need to know that this is eventually consistent system, which means that all writes will eventually be distributed across all servers. First, Ellie starts a session depicted here with a red circle, and then she makes 2 writes, W1 and on top of it W2. And the definition of Monotoinc Writes says that any client who would make the read from any replica, disregarding of any sessions they have or they don't have, they will see those 2 writes in exactly the same order, W1 and then W2. When another client Bob reads from server 2, it sees those 2 writes, W1 and W2, in exactly the same order they were posted by Alice. And when Bob makes a read from server 3, he sees only write W1. But in both cases, Monotoinc Writes guarantee is satisfied because order of the writes is the same. And it's perfectly possible that on replica 3, the second write it's just not yet arrived. The simplest implementation of Monotoinc Writes would be just making writes always on one replica by a single client. And in that case, this guarantee will be satisfied automatically. And such method is sometimes acceptable, but in some cases it's not acceptable because it has a very serious drawback of handling cases when some servers will fail. And if server fails, then client has to make a fallback. But when client makes fallback, it means that some writes might become non-monotonic because it might fall back to the server who don't yet have all the writes which were previously done by the client. And in that case, we will have violation of the guarantee. And in some cases, it's okay, but in other systems, it's not acceptable. Let's try to solve this problem by making the system which literally ensures that the definition of Monotoinc Writes is satisfied. The definition says that if some writes were done sequentially, then that they should be seen in the same order on all replicas, and that they should be propagated in the same order. It means that we need some way to keep track of our writes, and thus we will start with introducing write ID with which will be unique across all servers. Also, let's introduce a component, session manager, which will sit in between client and server, and it will be responsible for proxying the calls from client to servers and for selecting servers which would satisfy Monotoinc Writes guarantee. There are several requirements which must be satisfied on the servers, but they are quite reasonable and they could be imposed on most of the eventually consistent systems. It's obvious that a server must store the data, but apart from that, server must also store write IDs of all the data items. Apart from that, server needs to provide an interface to the client so that client could ask if server has some specific set of writes. And finally, there is a constraint that all writes must be accepted and propagated across all servers in the specific order they were initially made, which is called write order. The session manager's responsibility will be to keep write set where it will store widths of all writes made within the session. And during each write, session manager will have to iterate through all servers until it finds the one which contains all the writes in its write set. Let's see a simple example how it would work. We have a client, session manager, and two servers. And clients first wants to make a write. It sends a write request to session manager, and session manager forwards it to server 1. Server 1 assigns with 1 to this write, responds to session manager, and now session manager has to store this with 1 into its write set and respond to client that the write was successful. Next, during the second write, session manager has to ensure that it will satisfy Monotoinc Writes guarantee, and for this it iterates through all servers and checks whether they have all the writes present in its write set. First, it checks server 2 and it does not satisfy that condition. And then it checks server 1, which satisfies that condition. And because of this, session manager chooses this server to make actual write, and it makes the write. And again, as a result of the write, it has with 2, which is stored in its write set, and then the result is returned to the client. As you can see, non-monotonic write was prevented, and the algorithm works, but it has major drawbacks. First one is that servers and session manager has to store potentially infinite set of writes, and second, that session manager must send them over the network to servers. And in any real system, such sets that would grow infinitely with time, and it's not usable. But it's very convenient to use for illustrative purposes because it closely follows the definition, and also further it can be extended to more advanced version of the algorithm, which would work similarly but will not have all problems of this algorithm. Real industrial systems will use version vectors to achieve monotonic writes. And the main idea of this approach is that we will remove our major drawback, the infinite set of widths, and we will compact all of those widths into a small version vector. This version vector will contain a number of elements equal to the number of the servers. Each server needs to have its own clock. Those could be any type of clock, it could be real clock, Lampert clock, or just counters, and the only requirement to that clock is that when we are doing writes, any subsequent write would have associated clock value bigger than any previous write. So basically those clocks are always increasing with every write. Each server will have a vector containing values of the clocks of each other server, and in this vector it will be responsible directly only for one value corresponding to its own clock. When replication will happen between servers, together with the replication of the data, those version vectors also will be synchronized between servers. Each write will also have a unique write ID, but this time this write ID will contain two parts. First part is a unique ID of the server where the write was made, and the second part is the clock value of that server at the moment of the write. To make it work, we also need to define two operations on version vectors. The first operation is to check whether one version vector dominates another one, and to say that, for example, v1 dominates v2, we need to be sure that every element of v1 is more or equal to corresponding element in v2. We need this dominance relationship in order to session manager could decide whether this server is behind or ahead of its own state and choose the proper server which is not behind. Another operation is merge operation. When two version vectors are merged, we select maximum value corresponding to clock of each server in that version vector and just use that value in our resulting version vector. We need merge operation in order to update version vectors when there is replication happens between servers. And also we will use merge when we will merge server version vector into client's write vector after the writes. Now, when we know the basics, let's see how it works together. And for now, we will focus only on servers, leaving out what happens on the client side. Initially, we have two servers. Their clocks are zeros, their version vectors are zeros, their data storage is empty, and we have a set of writes coming in the specific order to those servers. When first write x equals 1 comes to the first server, its clock is incremented, its version vector is updated, and the value of x is stored in its data plane. The same process happens for the second write and for the third write. Next, there are two writes coming to the other server, server 2, and variable z is being updated. Also, clock of the server 2 is incremented, and the version vector of server 2 is updated. And at this point, we are in the situation when, by looking at version vectors, we can see that server 1 is behind of server 2 and server 2 is behind of server 1, because each of them has writes which are not present on the other one. Next, there is replication event, and all writes from server 1 are replicated on server 2, and the version vectors are synchronized as well. So now we can see that server 2 is ahead of server 1, and we can say it just by comparing their version vectors. Then we have opposite replication, and now version vectors are equal, and by looking at them we could see that those servers are in exactly the same state. Let's combine all of it into an algorithm. To make the write, session manager has to find a server which version vector dominates its write vector, and after each write, session manager has to receive most recent write vector from the server and merge it into its own write vector. And that's basically it. And for it, there is no specific logic, and the session manager just chooses any random server and makes the read from it. Now let's see an example how writes working. First, all components are in their initial state, and all clocks, version vectors, everything is zeros and empty. Client sends a write request to the session manager, and it forwards it to any random server, and in this case it's server 2, because by this time we didn't have any write in this session, so there is nothing to achieve, no guarantee, because it's the first write. But when this first write is made, clock of server 2 is incremented, its version vector updated, and returned to the session manager. And now session manager merges this version vector into its own write vector. And now during the second write, now it has to do something to ensure that Monotoinc Writes guarantee is satisfied. So it iterates through the servers. First, it gets the version vector from server 1, ensures that it's not dominating its write vector, and then it switches to server 2 and asks the same question from server 2, whether its version vector dominates its write vector. And this time the answer is affirmative, and thus session manager decides that server 2 is the one which needs to be sent the write request. So it sends the write, and as a result it gets back updated version vector of server 2, and again merges it into its write vector and responds to client. So as you could see, the guarantee is achieved, non-monotonic writes were rejected, and everything is working. This algorithm already works much better than previous one, but it can be optimized even further. Indeed, in the majority of cases, we don't need to switch between servers. One client could always use sticky session and work with one specific server. And in that case, session manager don't need to make all of those checks of version vectors on each request. And basically, we need to switch between servers only in case of failure of a server which we used before. And in case of failure, session manager just switches to another server using the algorithm we just described by finding a server with a suitable version vector which dominates its write vector. And to make this switch even faster, client could cache values of clocks of each server or their version vectors locally. And when failover needs to be done, it's done immediately. So unlike the just bare sticky session approach, we don't have this losing of guarantee during the failover. And unlike naive by definition implementation, we don't have to keep a huge infinite amount of data and send them over the network each time. We have just seen how to effectively implement monotonic writes on top of eventually consistent system using version vectors. For this, we have introduced Session Manager component, which is responsible for keeping write vector containing clock values corresponding to writes which we made in the scope of the session. And this component is responsible for selecting proper server to make writes. And each server additionally must keep only a small vector which has the number of elements which is equal to the number of servers. It's much more effective than the straightforward approach, and also it solves the failover problems when there are failures with some servers. I hope you enjoyed this video, and I recommend my other video about client-centric consistency models, which compares them and provides more thorough definition, examples, and use cases. And also I have more fundamental video about consistency in general, which covers why we need consistency models at all, what is linear reusability, sequential consistency, FIFO, causal consistency, and eventual consistency. And if you are interested in implementation of other session guarantees, just look at other videos on my channel. By this time, I'll have all of them described. If you found this video useful, you could subscribe to my channel and get notified when I publish my future videos about distributed systems. Hope to see you again. Bye.